Okay, welcome back everyone to the Fractional Calculus seminar series. Unfortunately, we missed last week's talk, but we are back again this week with Karel van Bockstal. He obtained his PhD in mathematical engineering in 2015 from Ghent University, Belgium, and is currently a postdoctoral researcher at the Ghent Analysis and PDE Center at the Department of Mathematics, Analysis, Logic, and Discrete Mathematics at Ghent University. His research interests are related to the mathematical analysis of evolutionary PDEs, as well as to the development of numerical algorithms and their numerical implementation. This research focus concerns direct and inverse problems in heat transfer, elasticity, electromagnetism, and thermoelasticity. He was awarded the EAIP Young Scientist Award of the 8th International Conference on Inverse Problems, Modeling and Simulation in May 2016. And today he is going to speak to us about inverse source problems for fractional diffusion equations. Please, the floor is yours.
Yes, thank you, Arran, for the kind introduction and for the invitation to present my work. So I will speak indeed about inverse source problems for fractional diffusion equations. Okay, so what I would like to do today is also to give an introduction for the classical heat and wave equations concerning the inverse source problems. So either way, we'll look in the first part of the presentation to determine the space-dependent part of the source. This will mainly, what I will present will mainly concern the uniqueness of the solution to the inverse problem. And the second part of the presentation is devoted to the reconstruction of the time-dependent part of the source, where I also will briefly explain next to the uniqueness of the solution how we obtained existence of a solution. So the problem I consider today is on the top of this slide. D beta tu is a capital fractional derivative order beta between 0 and 1, which is defined here. And operator L of t is a non-autonomous operator of second order. So it has this form. It means that the coefficients are in the problems we have considered are also depending on the time variable. So I work on a bounded domain omega with the Lipschitz boundary. The results are valid in general dimensions, and capital T denotes the final time. So these are the classical assumptions on the operator L and its coefficients. I assume that in the tensor A, the coefficients are an infinity on Qt. So Qt is omega times half open interval 0 capital T. And I assume that this tensor is uniformly elliptic. So this means that there exists a positive constant alpha, such that we have this classical inequality for almost all xt in Qt and for all psi in Rd. And C is also in an infinity and is assumed to be positive. And so we have two scenarios, as I mentioned. So first is that h of t is given in the source, that h of t is given, and we would like to determine f of x. This is the first part, and in the second part, I will assume that f of x is given, and I want to determine h of t from a suitable measurement. And these are inverse source problems, and there is a nice tutorial on inverse problems for fractional diffusion equations by Yin and Rundell. And section 3.3 in that tutorial is also devoted to inverse source problems. So this is what we'll start now with part 1. And as I said, I will first focus on classical diffusion equations. I will explain the main results concerning the inverse problems for the diffusion equation, also briefly explain how these results were obtained, and The main point is here to explain the energy estimate approach, and then I will show how this approach can be adapted to fractional diffusion equations. In this part, I will also discuss about a fractional wave equation. So this is a problem for the heat equation. So first order time derivative with respect to the temperature. And first, the basic stated basic result about the opposeness of the forward problem. So if the given source f tilde is L2 in time and L2 in space, and tilde U0, the initial data belongs to H10, then there exists a unique weak solution in the intersection of these two spaces and satisfying that the time derivative of U is L2 in time. And we will later see that this regularity of the time derivative is not satisfied for the fractional diffusion equation. There we will have that the time derivative of U is L1 in the time variable. So from the direct problem, we know that the solution at every time is well defined as an element in L2 omega. And so in the inverse problem, we want to find the spatial distribution of heat source from the final in time measurement, which is denoted by psi of t. So I have considered here a homogeneous Dirichlet boundary condition, and the initial data I will assume now, and also know that this is equal to 0, which is also the case when looking for the uniqueness of the solution. So with this inverse problem, can define input-output operator from L2 to L2, which associates with the f of x in L2, a of f, and a of f is a solution at the final time of the problem. So you solve this problem, 0 initial data, then this operator a is linear, and we can show that this is a compact operator, in fact, which is well known, resulting that the inverse problem is ill-posed in the sense of Hadamard in particular with respect to the continuous dependency on the data. So so the inverse problem is formulated as an operator equation, and existence and uniqueness of this solution of this inverse problem is studied in many papers, starting from the paper by Cannon, Rundel. You have book of Prilepko and Isakov, and also more recent work of Marian Slodička and Thomas Johansson. And so now I will go through these results and also give some details about the proofs, because it's good to remind. So this is first result, a paper of Rundel in 1980. We considered the autonomous heat equation, so L is time independent. And on the right-hand side, even part of the source H is equal to 1. So this is now the operator L. So the domain of L is H2 intersected with H10. And the coefficients AIG belong to C1 on the closure of omega, and C is contingent on the closure of omega. So in this paper of proof the uniqueness of the solution to this problem on the basis of the final and time measurement, the operator L doesn't need to be self-adjoint. So from the Lummer-Phillips theorem, that follows that minus L generates a semigroup of contractions, such that in fact the norm of this operator for any t will be strictly smaller than 1. So effect. So what we do is we apply here a semi-group theory. So there's a closed formula for this solution, which is given here. And so initial data is equal to 0. In the case of uniqueness, also the final and time measurement is equal to 0. And then you want to show that f is and also u both are equal to 0. So sketch of the proof is that you apply L on this formula. So first term is equal to 0, and f is time independent. So we can rewrite it in this way, this integral. So what we had here is I minus e to the power minus this operator e minus lt acting on f. So as this is a semi-group of contractions, we can invert this operator, and we get that f is equal to this expression. And if we look at final time, then we have that u of t, and also L of ut is equal to 0. So we get that f is equal to 0, which also implies that u is equal to 0. So this is a sketch for the proof of uniqueness. Then in the case that there is also time-dependent part inside the right-hand side, you need to assume that A is symmetric such that L is self-adjoint. And we note that a generator of the adjoint semigroup is minus the adjoint operator of L, so it's minus L. And this we can affect the main ingredients to show also the uniqueness. In this situation is in the case that either h is positive and nowhere 0, or h is negative. So u at final time is equal to 0. We take the scalar product of ut with f. So which gives this integral. Then from the semi-group property, we go to this equality. We have the joint operator, and so using that operator's self-adjoint, we get here also operator L. So we get a norm of this guy. And so if h is positive and nowhere non-zero, then we get that this is equal to 0, and so f is equal to 0, and we also conclude that u is equal to 0. Okay, so but here in this results, so the operator is time independent, and my main focus in this research was in the case where we have time-dependent operator, and then we need some other approach, which I call here the energy estimate approach. And for this approach, we need to assume that some high regularity of the solution, namely that the time derivative of u belongs to this Bocher space L2 and 0t h10. And I will explain here the main steps, and then later in my presentation I will only explain what's different compared to the analysis here. So suppose that u and f satisfy the problem. So with initial data equal to 0, final time measurement equal to 0, and then for uniqueness, we want to show that f is equal to 0 and u is equal to 0. So main trick is to multiply the PD with the time derivative of u to integrate over omega, and also to integrate over time from 0 to final time t. Then by interchanging the order of integration, we get f of x multiplied with u at, because f is time independent, u at final time minus u at time 0, which are both equal to 0. So the right-hand side cancels out. On the left-hand side, we will apply a Green's formula, which means in fact that we look for weak solutions. So after applying Green's formula, we get this identity, and we also supposed that H is strictly positive, such that we can divide by H. So if you first divide by H and then integrate in time, you get this identity. So the right-hand side is equal to 0, and we need now to conclude from this that this two terms are positive, and so we will in fact we will apply integration by parts on the second term on the left hand side. So we can rewrite the second term the factor 1/2 in this way. And then we apply integration by parts, so we get the derivative of 1 over h, and multiply it with the norm of the gradient u to the power 2 with minus sign, and then the boundary terms are given here. But these boundary terms cancel out because initial data and final time measurement are equal to 0 almost everywhere in omega. So this is cancels out, and so what's done in the works is this derivative is calculated, so we get plus sign the derivative of h divided by h squared, and then there is the assumptions made on the condition of the derivative. This was the first way, so it's assumed that next to h is strictly positive, that the derivative of h is positive, so this integral is positive, and then we get that this integral, which is positive integrandum, is equal to 0. So at h is strictly positive, initial data is equal to 0. We get from the point that the time derivative of u is almost everywhere 0, that also u is almost everywhere equal to 0. And then from the weak formulation from the PDE, you can deduce that f is equal to 0 almost everywhere in omega. So now I've showed this variation or energy estimate approach on the example with the Laplace operator, so also operator which is just time independent here. And what you see is that with this approach, next to the condition that h is strictly positive, you get also the sign condition on the derivative, which is an additional cost which occurs in this approach, because I showed you with the semigroup theory with the closed formula for the solution that we have in fact uniqueness of a solution to the inverse problem only under the condition that h is strictly positive. The advantage of this approach is that we, with this approach, also are able to study the inverse source problem with a time-dependent elliptic operator. So, but somehow disadvantage is the additional condition on the derivative of h. Note that if h is strictly negative and the derivative of h is negative, that there is also a uniqueness of a solution. So, and this regularity assumption is because we apply Green's formula, so we need that the gradient of dtu is well defined as an element in L2 omega. Okay, so now let me focus on the operator L, where we have that the coefficients in L depend on both the space and time variables, so a of x of t and c of x of t. And let us assume that elements aig are C1 on the closure of Qt, and that C is continuous of the closure of Qt. So we have no representation formula. We cannot use semi-group theory, and I have before in literature this energy estimate approach was used. Refers to the paper of Dyer, Sloditschka, and Johansson for the case h equal to 1. So we need to assume additionally that A is symmetric and that we have this condition on the square root of A, the square root, so A is uniformly elliptic operator is positive definite, so also the square root of A is well defined, will also be symmetric, has to satisfy this condition, which meaning in the case that D is equal to 1, that A is the time derivative of A is decreasing, and this condition we also need for C. Okay, so case H equal to 1. So in the paper of Dyer, H was equal to 1. Also already in not for a tensor, but for for A equal to A. Vex-T was already studied in work of Isakov with these two conditions I mentioned, and so also there it was need, so H was C1 on closed time frame, and so either you have H is strictly positive and the derivative is positive, or H is strictly negative and its derivative is negative. So also the conditions which were arising with the variational approach. So now what's the main point or main estimate we need to do for the time-dependent operator, and I will only show for a conductivity, so A of t. So we need to handle this term. We use that we can that we have the existence of the square root of A. That this tensor is also symmetric. So we have A 1/2 here, and we rewrite the second term in the derivative as the time derivative of A 1/2 gradient U, and then we correct with this term. So we get can rewrite the result as 1/2 of this integral minus the correction term, and then again on the first integral you may apply integration by parts. So we get minus sign, we get the derivative of 1 over h, we get the L2 norm of A 1/2 acting on the gradient of u to the power of 2. And here, so we assume h is strictly positive. Here you see the condition of the previous slide. So this is negative. So together with the minus sign, this is positive. And if h is strictly positive, then we also get that this first term is positive. And so this term is positive, and the same can be done for the term with where c multiplied with u. As an alternative is looking on the sign of the derivative of h. We have here, so we have the derivative of h divided by h squared. H is strictly positive, so we can look at the division of the derivative of h divided by h as well. And this was noted in a paper by Sloditschka and Johansson in 2016, where they looked at the function of t, and basically what they needed is that this derivative of alpha t is is negative. And this comes on the following reasoning. You can also maybe already deduce this from what I explained before, but I rewrote u divided by h as v, express the time derivative of u divided by h in terms of v and alpha, which was even the following PDE, where we have in front of vc plus alpha. And so we have seen that there is a uniqueness when the time derivative of c was negative. So now we need that the time derivative of c plus alpha is negative. So and for this they assumed that alpha prime is negative. And this extend uniqueness results also to functions which are not monotonic. So like positive concave functions like square root of 1 minus t, a bit away from 1, and then or t sinus t function. So this extended class of possible solutions. And then later on, a paper in 2020, Slodichka showed this he showed also uniqueness result, but for a special case of the time-dependent operator L, namely that you can factorize time-dependent part by function p of t. Here also additional term plus, so there's also convex, no, it's a cu divided p, also an additional term with a different function instead of p is considered, and then uniqueness is shown until the assumption that h is positive or negative, non-zero. But also this approach does not work when the a, in the general situation, a depending on t and c depending on t. Then briefly about wave equation, then I will go to the fractional equations. So a wave equation, Isakov showed that there is uniqueness if both h and its derivative are strictly positive or strictly negative. If h is equal to 1, there is no uniqueness of the solution. There's a counterexample in the book. And there is uniqueness in the presence of a damping term. So if we have additional damping term in the equation, then you can readily show the uniqueness of the solution also by a variational approach by multiplying with the time derivative of u, then this term will imply the uniqueness of a solution. So if mu is strictly positive, there is uniqueness under these two conditions. So here derivative may be equal to 0. And then the alternative approach when looking at this rational function alpha t, then PD in terms which is given here, in terms of v becomes this one, and then you need analog to the heat equation that the derivative of this term is negative, which is written here, and that this so this sum of these two guys should be strictly positive. And in fact, I made a proof for a higher order operator, but it's also valid for second order operator. Okay, so this was quite long introduction, I see. And now I will go to the fractional equations. So in the first part, results are based on these two papers. First one, I joint work with Marian Slodichka, Katerina Siskova, published in Applied Mathematical Letters. And second work, where I extended some results, including, I will explain what I mean with non-smooth solutions published in Fractal and Fractional. With non-smooth solutions, it's already on the slide. So I refer to the characteristical feature of Caputo fractional subdiffusion. A problem is that there is that there is no smoothness at initial time, because the time derivative of u will blow up. Noticed in many papers, Steins in 2017 showed estimates of the solutions for 1D problem with constant p, c depending on x. Showed this bound on the time derivatives of the solution. When we look at the time derivatives, so the first order derivative we have here t with exponent beta minus 1, second order derivative beta minus 2. And this is generalized by Pavan to general second order autonomous elliptic operator. So here we see that from this estimate we have that the time derivative of u is L1 integral in time and not L2 integral, which has some consequences. So the counterfractional derivative I've rewritten in this way. So k beta is the Riemann-Liouville kernel. This asterisk sign is the Laplace convolution, and yeah, I used some very nice properties of this kernel, namely it's positive, it's decaying, it's convex, which is in fact implying that should be k beta is certainly positive definite, implying this lower bound with the coefficient cosine of 1 minus beta multiplied with pi divided by 2. So it's getting closer to 1 when beta approaches 1. And here, if the time integral of the Laplace convolution, which is squared, and this is exponential minus t kernel. And basically, this result was shown for functions in L2. And we would like, we applied this result for, instead of u, for the time derivative of u. But as I mentioned, the time derivative of u generally does not belong to L2. But this result here is also valid if u is in L1 in time, and convolution of Riemann-Liouville kernel with u is L infinity in time. So then this integral is well defined. Also, convolution is almost everywhere well defined. And this is one of the key ingredients later on in the presentation. The second one is a result by Kubica and Yamamoto from 2018, where they showed when you have the Riemann-Liouville derivative applied with u integrated from 0 to s, we have this lower bound where we have kernel evaluated in t divided by 2, and here the L2 integral of u. And they show that this result is valid for u in L2, and k beta star u should be h1 in time. This was a similar result, so it's an extension of theorem of Sacher to the Riemann-Liouville kernel. In fact, was already shown also in a paper of Sloditschka and Siskova in 2016, but they used that also, the time derivative of u is in L2. So u belong to H1. And later on, I extended this result also for space-dependent variable order operators. So this is the inverse problem for fractional subdiffusion equation. So we look at reconstructing f of x from the final and time measurement, and with the operator you have seen many times before in my slides. Literature before all considering space-dependent coefficients, works of Sakamoto, Yamamoto, discussed the uniqueness of the solution, y, and one also regularization methods. Similar problems where there is a general kernel is considered are studied by Kinaj and Yano, also by Bajlakova. Multiterm diffusion equations are also considered. I will go quickly here. There are also numerical studies, and then Sloditschka also extended his result for classical diffusion equation to the fractional equation, but assuming time derivative of u in L2. So the assumptions for uniqueness are the classical ones, so all elements of A are C1 on the closure of Qt. A is symmetric, uniformly elliptic. C is positive. Also C1, we have this condition, and also the time derivative of C is negative. So the same conditions as for the diffusion equation will be sufficient also for fractional diffusion equation. So we have shown that there's uniqueness of the solution under this two conditions on H. So either H strictly positive, derivative positive, or this condition satisfied, and there exists at most one couple U of F in L2, UL infinity in time, H1 0 in space, time derivative of U in L1. So first, in our first paper, we showed for L2. Later on in my paper for space-dependent order operators, I showed the result also for time derivative of U in L1. And so we need, and this is satisfied for the solution of the direct problem to the subdiffusion equation, that the time derivative of k star u minus u 0. So, but u is absolutely continuous, is L infinity in time, so it can be written in this way. Okay, this I just mentioned. So in the case of uniqueness, again, we have that u tilde 0 is equal to 0. So we need to handle this integral and the other terms. So the approach was to multiply with the time derivative of u, to divide by h, to integrate over the space domain, and then to integrate from 0 until final time. So all the other terms we handled, the right side term was equal to 0. And then other terms were handled with integration by parts, and this we'll also do for the main term now containing the Caputo derivative. So after integration by parts, we have one boundary term with evaluated final time t, which is given here. So 1 divided by h evaluated final time, then this integral, and then we get minus time integration, the derivative of 1 divided by h again, and so, and the time integral of this function here, depending on the time variable. So now it's integrated over s, and so again, when h is strictly positive, we could divide. Now the derivative of h should be positive, and we have that the kernel is positive definite, so this integral is positive. And in fact, we will use a strongly positive definiteness on the first term. So what's in fact resulting in that we have that the convolution of e to the minus t with the time derivative of u is almost everywhere equal to 0 in Qt. And then from Fredholm integral theory, we can differentiate this. We get a second kind equation, so implying that time derivative of u is almost everywhere 0. And in this way also u is almost everywhere 0. And we get the uniqueness of the solution to the inverse problem. Because then also f is equal to 0. So key ingredient here is the strongly positive definiteness of the kernel. In the case that h is not strictly positive, so changing sign on the time interval, then in the paper with Sloditska-Siskova, we constructed a counterexample for the uniqueness of a solution in 1D. This is the problem. homogeneous degree boundary condition, we work on 0 pi for the space variable, 0 for the time variable. We take an eigenfunction of the operator satisfying g of 0 and g of pi is equal to 0, and we write a solution as g multiplied with the time-dependent part alpha. So we have already that the boundary conditions are satisfied for u, and we assume that alpha is equal to 0 at equal to 0 and 1, such that the measurement, so initial condition, is satisfied. So we now need that this u is satisfying the equation. So we trivially see that trivial solution is a solution to this problem. And we can also construct a non-trivial solution, which is changing sign. We have picked this alpha t with a parameter beta here. This defines h of t in this form. And then, for instance, for b equal to 0, 1, lambda equal to 1, and a fractional order of the derivative 0.5, we have that h of t is changing sign on the time interval. So we have constructed a non-trivial solution next to the trivial one, so violating the uniqueness of a solution to the inverse problem. Okay. I will briefly say here that you also can consider time average measurement of u in time. Then instead of multiplying with the time derivative of u, can multiply with u, integrate, divide by h, integrate in space and time domain, and then again using integration by parts, we can then you can use the result of Kubica and Yamamoto to have effect that L2 0t normal time of the L2 norm of u is equal to 0, implying also the uniqueness of a solution. So this is also a good, theoretically at least, a good measurement for the fractional subdiffusion equation. Nice to note about the fractional wave equation is that there is no damping term needed compared to the classical case, beta equal to 2. The main point is here. We can so we have now this definition. So beta is between 1 and 2. We can multiply with the time derivative of u. We get this as a first term in the energy estimate approach, and we can handle this term again by the lemma of the article of Kubica and Yamamoto. So in this way, all the other terms are positive. Right-hand side is 0. So other terms on the left-hand side, I mean, are positive. The right-hand side is 0. So this term is also less or equal to 0. So we get that the time derivative of u is equal to 0. And also for the fractional wave equation, there is uniqueness of a solution. But there is, due to the non-locality of operator, there's no damping term needed, which is a nice difference. Okay, now I will go to part 2 of the presentation, the reconstruction of the time-dependent part of the source. So first, for the diffusion equation, is to find h of t based on condition of over-determination. It's considered the weight function omega inside the measurement. This measurement is denoted by E of t, and you can consider Dirichlet and Neumann boundary conditions, but conditions on the weight function will be different. In case for a Dirichlet boundary condition, we will also need that omega is 0 on the boundary. For Neumann boundary condition, only H1 regularity will be needed. So the idea in this approach by Cannon and Lin, also later in the book of Prilepko, is to measure the equation. To measure the equation means to multiply with this weight function and to integrate over the space domain. Then you can apply Green's formula on the Laplace operator to reduce the regularity. So in the case of Neumann boundary condition, we get this expression where we assume that the integral of product of f and omega is non-zero, so that we can divide by this integral to get this expression. So in the case of Dirichlet boundary condition, there is no boundary term in the expression. You can apply second time Green's formula even to get here only L2 regularity of U. Then you need that the weight function belongs to H2 as well. So in the case of an autonomous operator, as before, so time-independent coefficient problem can be reduced to an integral equation of this second kind, a Fredholm equation of second kind. So starting from the closed formula of the solution and from the PDE, so we can apply L on U. Note in this case, so L is time independent. So we will so L is acting on this operator and F, so not on H. So we multiply with the weight function. I will very quickly integrate over the domain. We need to assume that the operator is self-adjoint, so A is symmetric, and then under the condition that this integral is non-zero, in fact, get this infinity. It's a Voltaire equation of the second kind, and so there exists a unique H to this problem. So under these conditions, and so when A is equal to 0 and the initial so measurement equal to 0, initial data is equal to 0, H is equal to 0. And so also when H is equal to 0 from the closed formula, get U is equal to 0. So but basically the approach is to reduce problem to Voltaire equation of the second kind for the autonomous heat equation. But also energy estimate approach works for showing the uniqueness of a solution. So here on the slide I've shown the example where we have homogeneous Dirichlet boundary conditions. So we have one of these two expressions for h of t. So we have the existence of some positive constant in first case. If omega belongs to h1, 0, we can estimate by c multiplied with the graded to graded of u. If omega belongs to the intersection of the spaces, we have L2 norm of u. But usually work with this first estimate, and so like a classical energy estimate, we multiply with u, integrate over space domain, integrate in time, apply Green formula, so we get this identity. And the right-hand side, you usually handle by a Young inequality or epsilon Young inequality, trace theorems, Nash inequality, Friedrichs inequality. But for classical heat equation, you put a small constant epsilon on h of t, the big constant 1/4 epsilon on scalar product of f and u of t. So you get this right-hand side, and some of the advantage of the heat equation that on the left-hand side, so you get L2 norm of u at the time point eta to the power 2 divided by 2. But such that terms from the estimate of h of t, so the gradient of u can work to the left-hand side. You take epsilon sufficiently small and then apply Gromwell's lemma, and there is you obtain that U is equal to 0 is also H is equal to 0, so uniqueness of a solution. But it seems that for the fractional diffusion equation, this information is not available. Remind that we have the strongly positive definiteness of the kernel, or lemma from Kubica and Yamamoto, resulting in that we have an additional integral here. And this additional integral will imply that we need to put a small, the small constant in epsilon Young inequality on this scalar product. And the results are in this two papers. There's also primarily other works which I will immediately mention. And my works are joint work with Ahmed Handy, first for a fractional subdiffusion equation. It's Journal of Scientific Computing, and later on we extended the results to multi-term fractional order diffusion equation in numerical algorithm journal. So what's the problem we have studied? It's the following one. So we want to determine the time-dependent part of the source. We consider the integral measurement on the complete domain omega. So this is maybe first restriction we have to make. This measurement is denoted by m of t. And in the right-hand side, still the goal is to consider generally f of u, but at the moment we are not able to solve this, and we needed this additional time integral of f of u. So we need an additional time integral to be able to show the uniqueness, but also existence of the solution, and also results only valid for Neumann boundary condition. The restriction on the operator L, I also will explain later on. So Sakamoto and Yamamoto, famous paper of 2011, considered also this inverse problem, considering bond measurement, showed uniqueness of determining h of t from the bond measurement. So as we will have to assume that the integral of f is non-zero, we have to assume that f in the bond measurement bond is not equal to 0. Numerical methods are later on studied in this paper by Wai and Zhang in a 1D paper. Also here, approach is to transform problem to Volterra equation, and they applied boundary element method combination with Tikhonov regularization. Then boundary measurement is considered by Wai and the co-authors in 2016, and also Tikhonov regularization method to solve the inverse problem. And then the same problem setting, exactly the same problem setting, was shown by Siskova and Slodichka. They showed the existence and uniqueness of the solution by Rothe's method, and it's this approach I followed also in our work. But they made some compatibility conditions on data, resulting in two strong assumptions, two strong compatibility conditions, and resulting in that the solution, time derivative of the solution is L2 in time. And our goal was to extend to the situation, like I mentioned, situation that the time derivative of u is L1 in time, but still we only partially solved this problem. This I will skip. Just to note that for the problem in case of linear f of u minus u, I took here with Neumann boundary condition L as constant coefficient, so we can have eigenvalues, can apply separation by parts, and we can get a solution of u as a series representation. It's even here, it's can be the Trieste series can also be written as a multinomial Mehta-Gleffer function, and from a paper of Srivastava from it was 1972, it can be shown that this series is uniformly bounded. Time derivative of u satisfied this estimate, which we also have shown before for the equation without this time integral of u. So the regularity assumptions we make we will make on the solution, namely these assumptions, and it's a measurement, are reasonable, and also it shows that we need to the result obtained in paper of Slodicka and Siskova may be improved. So what we did in our work published in Journal of Scientific Computing, we considered two numerical algorithms based on Rothe's method. We considered one on uniform mesh, one on a graded mesh, and for Rothe's method on uniform grid, we used convolution quadrature, and we could extend the class of solutions, also including non-smooth solutions, but with exponent gamma strictly larger than beta, the order of the fractional derivative. Over the graded grids, we made this assumptions on the solution. In fact, we needed this assumption on the solution to be able to show the existence of the solution, at least to show the convergence of the approximate solutions. The advantage of the graded grid is that, in fact, that the numerical results around t equal to 0 are much better, because it is problematic amount of finite grid can be considered. So the idea is to measure the equation. So in this way, an expression for h of t has been obtained in terms of the measurement and the solution of u. And we assumed that coefficient c in the operator L is only time dependent. In this way, you can, if you integrate over omega equation, we get c multiplied with the measurement. We have also the Caputo derivative of the measurement. Due to the Neumann boundary condition, we get from a divergence theorem that the integral of g over the boundary, and in the right-hand side we have this integral with this additional time integral. So we assume that M is absolutely continuous. And now I see the last 2 minutes, but I can go quite short. So this is the weak formulation of the problem. So we reformulate it as a coupled direct problem. So this is after applying Green's formula. This is an expression here for the bilinear form. So here we have h of t. H of t is expressed in this way. So if you substitute it, you get an equation for u. And so why this time integral? So the reason was that we don't have, as for the heat equation, when making energy estimate, this information on the left-hand side, we have either when testing, we have either we can use a strongly positive definiteness of the kernel or the result by Kucha and Yamamoto. And yeah, I will now shortly show how to use this result. So in the first case, I assume that f is linear in u, and then if first integrate the equation in time, and then you multiply with u, and then integrate in time again. So this is the expression for h of t in the case of uniqueness. So measurement is 0, boundary data is 0, with only one term. So from the operational formulation, we get on the left-hand side this 3 terms, and on the right-hand side we have this term. So this is coming from f of u. So k beta is strongly positive, implying that this integral is positive, and this is the reason why we need that effective. This is for constant coefficients equal for the coefficients equal to 1, but we need that the coefficient c is strictly positive. So h of t can be estimated in this way, also by using partial integration. So we need to put this small epsilon now on the term containing f, as I explained. And so there will be a big constant here. So if there would be no time integral, we would not be able to apply Gromwell's lemma. So this is the reason to have this, the need of this additional time integral. And so by fixing epsilon sufficiently small, we get that this integral is equal to 0, resulting the basic approach in the uniqueness of the solution. So we need that C is only time dependent and strictly positive. Otherwise, under this regularity conditions, so only competitive is defined in dual space, we are not able to show the uniqueness. If we have that derivative belongs to L2, 0 to L2 omega, then this is a variational formulation. We can work with a nonlinear f. We need to assume that it's globally Lipschitz continuous. I think that's classical assumptions. Then h of t can be estimated in this way, where we have the time integral now of the L2 norm of u, so not the time integral inside L2 norm. And then we multiply with u, integrate in time, and we use the result of Kabuchi and Yamamoto to have this L2 integral on the left-hand side, which is resulting in the uniqueness of a solution, because h of t, again, estimated in this way, and using epsilon inequality and the Lipschitz continuity of f, we have a same estimate for this term, and we get u is equal to 0 and h is equal to 0. So I will conclude presentation. So when you have this condition, only L2, only C should be positive instead of strictly positive, still time dependent, but still there's some room for improvement in part 2. So I assumed M absolutely continuous, that M was measurement was satisfying typical conditions, but instead of with the parameter beta, I took parameter gamma strictly larger than beta in the technical prior estimates which are involved in Rothe's method. I still believe this can be improved. Nice would be also for the diffusion equation to study the case when there is no connection between measurement and the Hibbe part of the source. And for part 1, there's still room for improvement by relaxing the monotonicity conditions on H. So I went a bit over time, but thank you for your attention.
Thank you very much for the talk. Let me ask, are there any questions or comments from the audience?
Well, can I ask you a question?
Yes,
Yes,
please.
yes.
Yeah. First of all, thank you very much for very interesting talk. Carl, in first part of your talk, we were seeing only uniqueness results. And
Yes.
in second part, we have both uniqueness and existence. How about in first part, especially when your operator, elliptic part of operator, depends on t? Do we have any result on existence of h of t? F
F
of
of
x,
X, yeah.
yeah.
Also for the Landweber method, the operator should be time independent. Then there's existence for time dependent operator. I don't think there is a result.
If
So
even doesn't depend on T
then
elliptic
it's
part.
then there are results if not depend on T, but then you need that operator associated with inverse problems is a small enough bond, but yeah, at the final time. So, but for time-dependent operator, I don't think it's possible to show the conversions.
Okay. Is there any to use if some Banach's fixed time theorem, fixed Banach theorem doesn't help?
I'm not sure. Mostly they're also for this is considered for a time-independent operator using formulas for the solutions in this situation. So yeah, it's a good question. Anyway, we can discuss this later.
Okay, thank you very much.
Thank you. Any
Thank
other
you.
questions or comments? I noticed that you mentioned several times some facts about this K beta function, which is essentially the kernel for the Caputo derivative.
Yes.
Would it be possible to generalize this work to some other kernel, for example, a Sonian kernel, or with provided some conditions are satisfied? Do you know what conditions you would need?
Yes, I'm looking in this problem to extend to Sonian kernels, but I will need similar conditions. So L1 kernel time derivative will be negative kernel, positive, maybe. Yeah, it is similar conditions as the kernel for the Caputo derivative. I try to look at this at this result, at this problem.
Okay.
Yeah.
I had another comment from slide number 49. Yeah, so this function defined by the double sum, so the function of t that's inside, that is a bivariate Mittag-Leffler function.
Yes.
Are you familiar with the papers about this?
Yes.
Yeah, it's also a particular case of
it's a
the multivariate or multi-index function, which I think was defined by Vezhlikova.
Yes, also in that paper there is uniform boundness. In fact, I extended some paper with doctoral student Frederik Maas, and we made some estimate on the multivariate Mittag-Leffler function.
Nice.
Where the before also in the paper, I think Yamamoto, the alpha decaying was for multiterm equation, and then alpha 1 was assumed to be strictly smaller than 1, and we extended that also to the case between 1 and 2.
Okay, great.
As an estimate.
All right. Any other questions or comments from anyone? Okay, then thank you very much, Karel, for the talk.
Yeah,
I will
thank you.
stop the recording here.